Hello and good morning. So today we're going to start looking at Chapter 5, which is an introduction to a new type of function called the logarithm. If you've seen this before, great. If you haven't, great. We're going to be diving into the structure of the log, where it comes from, how we can use it, and the cool applications that are out there that I think are kind of undersold in math courses, at least the ones I've taken. So logs are really neat. I'll explain a little bit about where they come from, and then we're going to jump into today some of their algebraic properties that make them nice to work with. And if nothing else, that's really what I want you to take away from logs, is that they're really nice to work with, especially when it comes to working with things that involve exponents, because that's what they're tied to. So where did logs come from? So they were discovered / invented around the 1600s, noticing the connection between bases and their exponents, and when you multiply them together to get a product, you end up with something that has the, I just erased it, something that has the exponent of the sum of the exponents of the factors. Right? What this allowed folks to be able to do is, instead of crunching through these tedious large calculations, right, like what's 256 times 512, before we had calculators, right, which was really, really recently if you think about it, we would have to do all this stuff by hand. So how this came about was people actually building printed tables with powers of certain bases on each leg, and then finding the result that they have in the table, and using this actually in a various number of ways. This is also a big way that slide rules were used. My grandfather built and designed train cars back in the 50s and 60s, and these guys were able to use slide rules, some of them still faster than you could use your graphing calculator today. And it all is based on using logarithms. So what they would do is find where their product was and map back to where the factors must have been, or vice versa. And again, there's also some variations of how you could use this, but it's a way to get quick calculations, approximate calculations that an engineer would be able to use, right, in a very short order. So one way that this would have been answered back in the day is to notice, well, 256 times 512, we could instead view this as 2 to the 8th power times 2 to the 9th power. And we would know from exponent rules that this is equal to 2 to the 8 plus 9th, which is 2 to the 17th power. And 2 to the 17th power, let's go ahead and calculate that real quick. So we'll get, 131,072. And so if you're able to break down your factors into powers and or bases with their powers, you could then just look up this entry for 17 and get your final result. And this would actually be broken down into fractional or decimal powers, and then you'd be able to kind of work your way through it. And we obviously don't use this anymore. Using log tables is a pretty dusty tradition, but the reason that we still use them is because they still allow us to simplify algebraic expressions, formulas, functions involving exponents in very nice ways. This comes into your aid greatly when it comes to calculus. But this is kind of where it came from. So that started with this through, again, this key idea that when you multiply two bases of the same base with different powers, you take the sum of their powers. So that gives you an easy way to kind of construct a table around that. So this is initially credited to a mathematician by the name of Napier back in the 1600s, but this, like a lot of things in math, this kind of popped up in different places all around the same time, which is really interesting. So let's take a look at the definition of a log, now that we know kind of where it comes from, what the motivation behind it was, and why we're doing this right after the exponential functions unit. The properties, which are going to be really, really important. It's probably the most important thing that you'll take from this unit, moving into calculus. And then the different types of logs. So we have the natural log and the common log. I said those backwards, but we have the common log, or what's also called the Briggsian logarithm, and the natural log. So let's dive into the definition and then some properties. Okay, so the definition, first I want to start off with this note here, which is that log x is a function. It's not a number. It's not something that can be canceled. Sometimes I'll see people just like crossing out logs when they're dividing because it seems like some algebraic thing or some variable. It's not a variable. This is a function. So in the same way that you have y equals f of x, here that function is the log function. So it has an input and an output. So what are the inputs and outputs for the logarithm function? Well, first let's state that it is the inverse function to the exponential functions. Here, this is what we call the common log. Which means it is the inverse to the function y equals 10 to the x. We use the base 10 number system. That's the most common number system that we use. So this is why it's called the common logarithm. We're often interested and we can do calculations a lot easier when things are base 10. So common log means it's the inverse to y equals 10x. So the reason I write this, that it's the inverse of this function, is so we can think about the inputs and outputs, right? So when we think about y equals 10 to the x, the input is the exponent, and the output is the number we get when we raise 10 to the input, right? So it's that number that it gets mapped to. So the input is the exponent, the output is the number that 10 is to that power, right? So this is 10 to the x, or 10 to that number. So the inverse of that then, y equals log x, or what we call log base 10x. We'll write it in the subscript here. What this means then, the input is the output of the exponential function and vice versa. The output is the input. So what does that mean? The output here is the input. Let me do it in green. The input of the other function was the exponent of 10. And the output was 10 to that number. So the way I tell my students to read this piece here in English is y is the power of 10 that gets you x. Okay, so here's an example of what that means. So log of 100 equals 2. Why is this the case? Because the output here, 2, is the power of 10 that gets you the input here, 100. Right, and we know this because 10 to the 2, we can do that in green here, 10 to the 2 equals 100. So this is how we understand it. And this is the kind of switcheroo on representing this relationship between exponential form and logarithmic form. Okay, so log or common log, sometimes it's written this way, most of the time it's written this way, is the inverse to 10 to the x. Okay, so the input and output get switched. So what's inside the log is what you get when you raise power to when you raise 10 to the power of whatever y is. Okay. So how this would another way to really think about this, since this is still in terms of x and y, would be that this is, if we wanted to keep the variables the same, x equals 10 to the y. Right? And now hit pause and see why that makes sense. Right? That x is 10 to the y. Y is the power of 10 that gets you x. That lines up with what we've seen here and here. Right? 10 to the y equals x. Okay. Just to be abundantly clear, the reason I'm going over this and over this is because this is a place where students get confused quickly, because we're now switching inputs and outputs on something we've been practicing a certain way, and it can get a little confusing. So this is the definition of log. Now I'm going to expand this to be more general, because that's the common log. This is for any base b. This is the inverse function to y equals b to the x. Another way you could think about it is, we usually don't write it this way, but it can be helpful, right, to see that this is really connected to this, right, because the input is the output, since they're inverse functions. And we'll have some more discussion of inverse functions later on, but for now, just knowing that switching the inputs and outputs is how you get an inverse function is fine. It's a little bit more complicated than that, but not by much. So this is for a general logarithm of base b. So to give an example here, okay, so like we had before, the logarithm base 2 of 256 is 8. Right? And why is that the case? Because, well, let's do it this way. X equals b to the y. Here's log b of x equals y. So base to the y, 2 to the 8 equals x, 256. 2 to the 8 equals 256. So seeing this relationship here, just getting used to the notation. So that's the definition of a general log of base b, and we have the common log of base 10. I'm going to do one more here because it's just such an interesting base, and we just finished working with it, which is what we call the natural log, and that's y equals log base e of x. We know that e is a really special base, right? Tied to what? Continuously compounding interest. That's where it came from. And so if we have log base of e of x, what does that mean? This is y is the power of e that gets you x. And since there's no nice powers of e, because e is an irrational number, I'm not going to highlight this with an example, but we'll go through a few later. But I just wanted to give you the three kind of types of logs we'll be playing with in this chapter. The natural log, which is base e, the common log, which is base 10. Those are the most two common. But there's also times when we want to switch the base, because if you're talking about things that can be factorized into different factors besides 10 and e, then we'll probably want to use those logs at some juncture. So it's kind of, think of it as like a Swiss Army knife for undoing exponential functions, but we got to be considerate of the base that we're playing with. Okay, so that's definitions, and now I want to move into properties, why we care about these things, and how they help us simplify complicated formulas. Okay, so the properties of logs, these are things that I do want you to memorize. Why? Because it's going to make things a lot easier. If you're recreating the wheel every time when you're working through a problem, it's going to be a rough go. So a couple flashcards, there's only about 5 properties, and you will thank me later, that's fine. But just believe me that you're going to want to memorize these. So these properties, what I'm going to do, I'm going to show you what the properties are. I'm going to give you a loose connection to where they kind of come from, and I'll show you how they work, one example of each. I'm not going to derive where they come from because we're not probably all interested in that, but I will link a video in the notes on where these things come from. So if you're a math major or you're going into deeper mathematics, this will be something you actually do want to watch. But for those of us who aren't, it's probably unnecessary, and you can just believe me that these will always work out. So here's one important property that you will want to know. Let's first give ourselves the relationship here, which is for log base a of x, let's use b because we're using that before. Log base b of x equals y. This is connected to the exponential relationship x equals b to the y. Right? Y is the power of b that gets you x. So keeping that in the back of our minds. So the first one we'll look at is if I have log base a of some u to the n. Okay, so there's a lot of notation here, but stick with me. This is equal to n times the natural log, or the log base a of u. This is not the natural log, but it does hold for that. This holds for all base a. Okay, all of these properties. So it'll work for base 10, it'll work for base e, and any base that you put down there. So what this says is that the log base a of u to the nth power is n times the logarithm of that base. So let me give you a quick example. So if I have log base 2 of 3 to the 4th power, okay, it's not going to be a super nice number because 2 to some power probably isn't going to get me 3 to the 4th. In fact, it won't. But what this allows us to say is that this is equal to 4 times the log base 2 of 3. And now that gives me some helpful information, right? Maybe I have some idea of what this value is. I could multiply it by 4. I've got a quick estimate ready at the go. But this also will just help us kind of massage and work out formulas like I've said before. But this is how it will work in practice. Another way to do this, which can be a lot more helpful, is let's say I had common log of 10 to the 5th. Well, what do we see here? Well, common log is really base 10, right? We typically don't write it, so I won't here. But this says that this is equal to 5 times the log of 10. And log 10 is something that we know, right? Log base 10 of 10, we should know that, or we will know, that this is 1, right? What is the power of 10 that gets me 10? 1. So this equals 5 times 1, which is 5. So the log of 10 to the 5th gives me 5. So that's really nice. And so much so that this is even its own property. So we can jot that down here, that when you have the same base, log base a of a to the n, this is just equal to n. And this should make sense with what I said before, which is, right, if the logarithm is, this number is the power of a that gets you this inside number here. What's the power of a that gets me a to the n? it's n, right? Don't overthink it too much. So that's why this property should always hold up. So as an example, if I have log base e of e to the fourth, let's do a different power, e to the fifth, which we also write, I haven't shown you this yet, ln of e to the fifth. It means just log base e. These are the same things. What is the power of e that gets me e to the fifth? That's just 5. So that's kind of a way to speed up this process up here using this property. If you already have within the function of log the same base as the logarithm you're taking, this will always simplify to whatever that exponent is, and it has to. Okay, third one. So if we have log base a of some a times b, this is equal to log of big A plus the log of big B. This also holds up for natural log, right? Again, this holds up for all bases of logarithm. This will always be the case. And this should somewhat remind you of the rule all right, I forgot 10 to the a times 10 to the b. This becomes 10 to the a plus b. There's definitely a connection here. And again, if you're interested in seeing how they really tie together, go check out that derivation video that I'm linking in the notes. But this is a rule that we'll also use to simplify logarithms, to go both ways on the equal sign, as I like to say. All right, sometimes we have maybe 2 logs and we want to condense them together. Other times we want to break stuff apart because it might be easier to have things be separate, right? Think of just if you've ever played with Legos before, it's the same principle. Sometimes we need things together, other times we need them apart. So this works for log base a and for log base e, log base 10. And so as an example, how this might look, if I've got, let's say, log base 2 of, let me do it like this, 24. And I want to break this apart. Well, one way we could do this is see that 24 is really 8 times 3. So maybe I could break this apart using this property, saying, all right, well, this is going to be equal to log base 2 of 8 then plus log base 2 of 3. And what's log base 2 of 8? Well, isn't 8 2 to the third power? So using our property above, so log base 2 of 2 to the third, we still have this log base 2 of 3 here. We should know that this value equals 3. Take a moment and see why that's the case. That has to be 3. And then plus log 2 base 2 of 3. Okay, so why this is helpful. Again, the splitting apart of some expression into little pieces is nice, and also it can help us get an idea of estimation, right? I know this number is going to be a little bit bigger than 3, right? What is log base 2 of 3? This is something a little bit bigger than 1. So really I'm looking at something that's probably a little bit bigger than 4, like 4.1 or something like that. So this helps me get an idea of where I'm at. So there's lots of different reasons why we'd care about this. And again, we're not using log tables like they did in the old days, but it helps to just have a sense of where we're at, right? What we call number sense in the biz. So this also works with natural log, and I'll do an example there. So if I had natural log of, let's say, 6, maybe I could rewrite this as a natural log of 2 times 3, which I can then break into the natural log of 2 and natural log of 3. And there's a few problems in the textbook that will have you practice this skill of representing a given logarithm in terms of other logs, because it might be you know those logs, or this log pertains to another function that we care about. Substitution and re-representation, I've said it before and I'll say it again, huge in Calc 1, 2, and 3. Literally makes the difference between what we can do and what we can't. So this is one way to do that breakout for ln of 6. And again, if you're given something like this, you know you could map it back. So I'd really like you to get good at going both ways on the equal sign. That's a key indicator to me that somebody knows what they're doing. They understand algebra, if they're able to go both ways and not just one way. All right, and the last one we'll look at for now perhaps is log base A of some quotient is equal to the difference of the logs of each of those. So how this looks in practice, and again you could think this is somewhat connected to, right, 10 to the A over 10 to the B. Maybe I should use different letters here. 10 to the N over 10 to the M is equal to what? 10 to the N minus M. Seeing that quotients are related to the difference here when it comes to exponents. So let's look at an example how this works out in practice. So say I had log base 3 of 27 over 36. How could I break this down? Well, I'd start by saying, okay, this is equal to log base 3 of 27 minus log base 3 of 36. And for each of these, this is supposed to represent the power of 3 that gets you 27. And the power of 3 that gets you 36. Well, the power of 3 that gets me 36 is not a easy to find number, but this one is. The log base 3 of 27 is 3. Right, because we know 3 to the third power is 27. So that must equal, it is equal to the exponent 3 minus log base 3 of 36. So here we just demonstrated how to use this property, but we can keep going a little bit further using the previous properties. So using the previous properties, we know I could break this up. Right, what is log base 3 of 36? We're just chasing down this idea. I could say it's equal to 9 times 4. And why am I using 9 and 4? Well, I know that 9 is 3 squared, right? 3 raised to some power, I can get to 9. So that would allow me to, when I split this up using the above property from number 3, splitting the product, I know that this is equal to 2. And so we get 2 plus log base 3 of 4. So this now is being substituted in here. And so we'll get this is equal to 3 minus this whole quantity, right? Because I just did this whole number being substituted out. So I need brackets because now I have 2 terms. I'm such a good math student using brackets like that. I'm such a pro. And then from there, distributing that through, so 3 minus 2 minus log base 3 of 4. This 3 didn't change, right? And then 3 minus 2, so I'm left with 1 minus log base 3 of 4. So I know if log base 3 of 4 is some number, again, it's probably a little bit bigger than 1. Think about the exponent of 3 that gets us to 4. It's probably just a little bit bigger than 1. 1 minus that number, I'm probably at like negative point something. So let me verify too, so I'm not just making things up. So we see here 1 minus log base 3 of 4 is negative 0.26. So I actually underestimated a little bit what this power would be. Log base 3 of 4, 1.26. Okay, so we have some idea of where this number lands just by reworking it using these properties. So let's look at the last property that we care about, which is what we call the change of base. So this can be a lot of kind of algebraic stuff, so hit pause, make sure you're making flashcards after the lecture, because each of these are important in their own right, and you'll need to use them in conjunction with each other, which is the most important, right? Like you've seen me kind of modeling that behavior here. So change of base, sometimes we don't want to have a log be in a certain base, whether it be we want it in base E or we don't want it in base E. Again, it depends on the problem. And so the change of base formula looks like this. Log base A of x equals log base B of x over log base B of A. Okay? Again, why this is the case, I'm not going to go into because it's only really interesting for the pure math majors, and there's not that many of us. So sorry, math majors, I feel your pain. But again, you can go check out that side video. What you really need to understand and mechanize and recognize, that's one word I just made up, you're welcome, is how this works and what the notation means. So base A, you see here the relationship in the denominator. I'm taking the log of A and I'm changing the base to some B, and I still have my input here, x. So let's look at an example to kind of clarify what this means. So if I'm taking the log base 3 of 10, and I want to change this to base E, because I'm working with E a lot, let's say. Well, then I would change this to be log base E, or ln. Either way you want to write it is fine, but get used to writing ln. ln of the input over log base B, or ln of the previous base, which is 3. Okay, so ln of 10 over ln of 3. So we might already have ln of 10 or ln of 3, or we just might need it in terms of natural log. So here we are, we've got it, and this might be a little bit easier to evaluate or estimate, whatever it might be. If I took the same problem and maybe change it to base 10, because one of the input here is 10, so maybe I want to simplify this and get my head wrapped around what is the size of this number. So how would this look? Well, it'd be log base 10, I can write it like that if I want to, of 10 the input, all over log base 10 of the previous base, which is 3. All right, and again, we typically don't write the 10 for common log, so we get common log of 10 over log base 10 of 3. Well, I know up here this is equal to 1, so this is really 1 over log of 3. So again, for whatever reason, maybe I wanted this to be expressed in terms of log of 3 instead of log base 3. Maybe I have a table for base 10 log of 3 and I can figure out what this number is. But either or, these numbers are going to be equivalent, right? That's the thing about this, is that we're not changing the values, we're changing the representations. This is how we re-represent a log in terms that we want. And again, this is going to feel like a lot of skill and drill, and it is, and we'll get into applications later on once we can kind of play with these things. So those are the main properties of the logarithm: how you change base between different logs, how we can split up quotients inside the logarithm, how we can split up products inside the logarithm, and how we can deal with powers inside the logarithm. So you can see how maybe all these things kind of play together and can be used in conjunction in different problems. Now I'll give you some quick pitfalls that I see happen a lot. So pitfalls to avoid. Because they play so nicely with addition and subtraction and multiplication and division and playing with exponents, that it can become confusing, or you could misapply these properties in a place where it doesn't work. So in other words, to know that, right, remember that ln of a over b is equal to ln of a minus ln of b. So this is true. What's false is when I see students say ln of a over ln of b, this is equal to ln of a minus ln of b. We might want to split it like that. This is not true. Okay, so what's the difference that you can kind of show your brain right now? That the quotient is inside the function. Okay, so same thing with the product rule. ln of a times b, this is equal to ln of a, the sum of the logs. But if I have ln of a times ln of b, this is not equal to ln of a plus ln of b. We can see how these things are different, maybe just at the surface. And again, what's the difference? Here, the product is inside the function, and that's what makes it work. Okay, so those are two common pitfalls to avoid. You might want to write these down just so you're not tempted to use them that way. So now that we have these properties and you practice them a little bit, I want to show you an application that is directly interesting to us, because you remember last unit we weren't able to solve for the input for exponential functions algebraically, right? We had to solve graphically only. So using these properties of logarithms, we're able to get into the input of an exponential function because it is the inverse operation or inverse function to exponents. Right? When we were solving equations before, plus and minus are inverse operations, times and divide are inverse operations, but what undoes exponents? Logs, right? Logs undo exponents. So let's say we had a problem, we had similar problems to this, where it was, how long for a $1,000 investment to become, using caveman speak here to kind of speed it along, how long for a $1,000 investment to become $6,000 at 15% annual interest? Let's say we got a really aggressive portfolio out there. Don't share your secret. So how do we do it? Well, that means our output was 6,000. Our initial value was 1,000, and we're earning 15%, and we're looking for t, right? How would we solve this equation? I'll show you the general process. You want to isolate the variable just like you did in algebra all the way up through pre-calc. Isolate the variable. So what does that mean? Well, if I had some constant term over here, I would subtract that from both sides, which I don't, right? So we don't have that, so I want to now divide by any coefficients. That's what I mean when isolate the variable. So I'll divide both sides by 1,000. And what do we get? 6 equals 1.15 to the t. Then think about what property of logarithms would help me get at that exponent. I will scroll up here. How about this one? This is the one we'll use most often for this purpose. And I'll write it out in clear terms. What it allows us to do is, if you take the log of some a to the t, we get back t times log a. That's big, because now we have access to the input variable, right? It's being multiplied instead of being raised as a power. But we can't just do that, right? We can't just take the log of the right side. We need to use the balance principle. Use log's property 1. So, in other words, if a equals b, we know that the log of a must be equal to the log of b, right? If it's a function and the inputs are equal, then the outputs have to be equal. So this is kind of the logic we're going to be using here. So then we bring this down and we say, all right, I'm going to take the log of 6 on the left, and on the right I'm going to take the log of 1.15 to the t. And then over here I'm going to use that property of logs to rewrite this right-hand side. So on the left I've got log of 6. On the right I've got log of 1.15 to the t is equal to t times log of 1.15. And how does that help us? Well, log of 1.15 is just some number, right? So I can now divide both sides by that number to isolate t. So now I'll divide both sides by log of 1.15, again, whatever that is. And we'll get log of 6 over log of 1.15 equals t. And then we can go into our calculator and get a decimal approximation. And so we'll punch this in, log of 6 over log of 1.15, and we get 12.82. So we get 12.82 years it will take $1,000 to earn $6,000, or to turn into $6,000. So this is how we use logs to solve for the input. Again, it will follow this general strategy where you need to isolate the variable first. Again, if there are other constants or other variable terms, or there's variables on both sides of the equation, you're going to need to use some algebra and some properties of logs most likely, or some properties of exponents to condense it and get it to where you want so that you can follow through this process. So there's going to be some practice with that. But we've covered a lot of ground. Where logs come from, why we still use them, their definition, properties, right, and the different types of logs. The common log and the natural log are the most common that we'll use, but again, using other bases obviously makes sense when we think of logs in this way, right, that it's the power that gets you the number inside the function, the inverse of the exponential function. Great. So enjoy your practice, and we'll see you in the class discussion.